There we go. Okay, so again, this is our normal distribution, normally distributed. We know that if you randomly sample this, that you'd expect more of the people that you selected to be close to the mean, the population mean, and that as you would expect fewer and fewer people that you sample to be further and further away from the population mean. In other words, blood pressure, you would expect most of the people to be close to the average blood pressure, and then fewer and fewer people have a relatively lower or much lower blood pressure, or relatively higher or much higher blood pressure. Okay, and since this selection is based on chance, if we take a sample from this population, we would expect it to display the same kind of distribution. In other words, if I took 100 people and found the average for those 100 people, blood pressure for those 100 people, I would think that I would be even more likely to be close to the mean simply by taking a large sample. Okay, if I took a smaller sample, I'd expect it to be closer to the mean than any individual in the population that I might sample randomly, but not quite as tight around the mean as say a sample of 100 people or 1,000 people or 10,000 people. They would all be more representative of what the mean would be. Ultimately, you take everybody and you have the population and you know exactly what the mean is. Very rare case for us. Problem is that we never really work with the population because we just don't have all that data. So we're forced usually to work with samples from a population and make predictions based on that, not the least of which, what's the mean of the population based on the mean of the sample. So now, if I were to do that, if I take a sample of size 25 from this population, I want to really know, well, how likely is it that that sample of 25 people is really going to be representative of the entire population? Or if I take a sample of 100, how much more representative of the population is that sample than a sample of 25 would have been, let's say? Okay, so we need that relationship. We have to understand how samples work. Okay, one of the ways that we might be able to interpret or learn about how samples work is to take many samples and see how they distribute themselves. So, for instance, one of the things I might do here is I might say to myself, well, I'm going to take repeated samples from this population of size 100. Okay. And if I might get, for instance, for blood pressure, I might get while blood pressure might vary from 70 to say 130 within this population, the average that I would get if I randomly sample 100 people is not going to be that broad because it's very unlikely that all 100 people would come from down here or all 100 people would come from up here. So a sample of 100 is likely to be very close to this mean. So, for instance, I might get 102 and 107 and 98 and 99 and so on and so forth. But if I took a sample of 100 people from this population, well, the first time I might get 102. Do it again, I get 107. Do it again, I get 98. Do it again, I get 90, 99, and so on and so forth. If I did this over and over and over again, thousands and thousands of times, maybe even an infinite number of times, right? I would get if I took these new means from this sample distribution, I would get a new distribution. And this is a distribution of sample means, right? It's no longer the distribution of the actual people. This is the distribution of sample means. Okay. So as we would expect, I mean, it really doesn't seem that much of a surprise that the average for repeated samples, the average mean we would get if we did this sample of size 100 over and over again, that mean, right, that mean, that X bar over here, that mean would be the same thing as the mean of the population. In other words, 100. If this was 100, if this was 100, then this would be 100. And that's if we took many, many, many uh, 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 samples of size 100 over and over and over again. Okay, so now we do see that there's going to be a difference now in the width of this distribution. Here, this represents everybody in the population. Everybody who might have a blood pressure from 70 all the way up to 130. Okay, while this represents the width of the likely distribution of sample means. Well, if I take a sample of 100, I'm never going to get all 70s because there's only a few people that have 70, right? There might not even be 100 people that have a blood pressure of 70 in this population. So I know that my width is going to be much narrower. Well, we know that this standard deviation for the sample means, I'm going to call it standard deviation of sample means, has a relationship between there's a relationship between the distribution, the width, the variability in the population, and the variability within these sample means. The wider this distribution is, the wider our sample mean distribution is. In other words, if this had gone from 10 to 200 for the population, then this would be a wider distribution, right? Makes sense because then we would get more people lower or higher, more extremes occasionally. Okay, so the other thing that it's dependent on is the sample size. Bigger the sample size is, the more likely we're going to get a value that's very close to the mean. Bigger the sample size, the more and more accurate is going to be our sample in terms of excuse me, predicting the mean. Okay, so there's two relationships: the standard deviation, right, of the population, and the size of the sample. And in fact, our standard deviation for this distribution, this new one, is going to be equal to the standard deviation of the population against sigma. I use that for the population. Okay, it's a parameter, okay, over the sample size, over the square root of the sample size. It's not directly related to the sample size, but the square root of the sample size. Since this is a fraction, the numerator, as the numerator gets bigger, the standard deviation sample means as the spread gets wider, this gets bigger. As the sample size gets bigger, since it's in the denominator, as the sample size gets bigger, this gets smaller. So they kind of have the opposite effect. Okay, so now we give this a special name. Instead of calling it standard deviation of the sample means, we call it the standard error. Okay, would have been nicer if they called it that, right? Because it would have been a little bit more descriptive. So, is everybody with me right now to this point? How do we feel about that up to this point? How about a comment or two? Okay, good. Okay, we're all pretty comfortable with that. So now we're going to go ahead and apply this. Okay, and the way that we're going to apply it is we're going to say to ourselves, you know, when I learned the empirical formula, I learned this relationship between the sample distribution, the mean, and the number of standard deviations away from the mean. What the distribution of how a normal distribution spreads out, where the population within normal distribution is going to be based on its standard deviation and where the sample mean, where the center is. Okay, I'm going to use that same relationship to my new normal distribution, which is the sample means. Okay, so I'm going to go get another piece of paper here. Here we go. Okay, so now this is going to be my distribution of sample means from the problem before. Okay, now we said that the mean blood pressure was 100, so my average, if I took repeated samples, in one case it might be 100, in another case it might be 106, 107, 98, 92, 101. I'm just making some numbers up here. But I know if I took enough of these, if I took an infinite number of these over and over and over again, then some of them, half of them would be below 100, half of them would be above 100. They'd be symmetrical, and they'd be normally distributed. Okay, so I know that my sample means, my means of all my samples is going to be 100. Okay, if I took enough of them. I don't know if I just took one sample, I don't know where it might wind up. It might be below 100 or it might be above 100. If I'm really phenomenally lucky, it might be exactly 100. Okay, but there's no way for me to predict that ahead of time. What I can predict is that there's a 50% chance that it's going to be below 100. There's a 50% chance it's going to be above 100. I can also predict that it's going to be, let's see, that there's a 68% chance that it's between one standard deviation of the sample means below the mean of all the sample means, and one standard deviation above all the sample means, 68%. Okay, because that's the normal distribution. That's my empirical formula. Okay, so now that's pretty powerful information. I don't know exactly where it's going to be. It's going to be within that range, let's say, for one standard deviation. So now I can use this, and let's say, take a look at something that might be more interesting. 2 standard deviations below the mean and 2 standard deviations above the mean. Okay, that represents 95% of the sample means that I would get from that population. I would, at 95% of the time, I would get a sample. If I took a sample from the population that we looked at before, okay, I would, at 95% of the time, I would get a sample mean that's between 2 standard deviations below the mean and 2 standard deviations above the mean. In reality, we know that the empirical formula is just an estimate, right? So it's really 2 standard deviations below the mean and 2 standard deviations above the mean would really give me something like 95 point, maybe 2 or 3%, right, of the outcomes that I would get. I would get some that were below and some that were above. I would get a couple of percent, 2 point something percent of that of the time I would get a value below 2 standard deviations below the mean, and about the same, but symmetrical, I would get a result above the mean. Okay, still with me there? Any questions on that so far? Okay, all I got is a new new distribution that is based on sample means, and it has the same properties as the old one. Only thing, it's narrower. The mean's in the same spot, but it's going to be not as wide a distribution. You guys okay on that? Just give me a good or okay, or I can still hear you. Okay, good. All right. So now, we just kind of this average, we can only live with the estimates for so long. So I just mentioned that really 2 standard deviations below the mean, 2 standard deviations above the mean really is a little bit more than 95%. So if we really want to look for 95% of the possible outcomes, instead of using 2 standard deviations below the mean and 2 standard deviations above the mean, you really use 1.96 standard deviations. Right? So instead of saying, oh, 95% of the outcome, 95.3% of the outcomes are between 2 below and 2 above, I'm going to stick with my 95% and just adjust my number of standard deviations instead. It's more convenient for me to be able to discuss studies talking about 95% of the outcomes than talk about 95.3% of the outcomes. Okay? So that's really the only adjustment that I've made. So now what is that based on? Well, that's based on the way that normal distributions are spread out. And what is that based on? That's based on a formula that gives us our ZTable. I'm going to open up the ZTable. Okay, here's the ZTable. And I'll close the bill. You don't need to pay for that bill. Okay, so there's my ZTable. These represents all the areas to the left. See the little shaded area? To the left of whatever z-score. This is the percentage of people that are in your study that are to the left of that z-score, that are so far away from the mean to the left that they're in this area down here. Okay, you could look at it 2 ways. This is the percentage of the population that's represented below that z-score. It's also, you could look at as the probability that if you were to just pick one person out of this whole population, what's the probability that they would be down here? So either way of looking at it is perfectly adequate. Okay, so let's look. These represent the areas that purple section represents. So let's look at that 1.96 negative, since we're to the left, negative 1.1, 0, 1, 2, 3, 4, 5, 2.5%. That purple area represents 2.5% if it's 1.96 standard deviations below the mean. Well, we said 95%, so 2.5%, we got another 2.5% to account for. So that other 2.5% is represented by the symmetrical area at the top of the distribution. So if the purple area down here is 2.5%, and plus 1.96 standard deviations above leaves 2.5% left over, then the area between negative 1.96 and positive 1.96 is, as we suspected, 95% of the distribution. Okay, so that's how we got that number. Now, if I was interested in the middle 95% of the distribution, excuse me, 90% of the distribution, well, then I would have 10% left over, but I have two tails to take care of. So I would want, see, 5% in the bottom tail and 5% in the top tail would leave the middle 90%. Well, if I look for the middle 90%, that would have to be 5%, right? So 5% turns out, an area of 5% turns out to be around here. And what is that? That's 1.60123. We're gonna, I'll stop at 4. It's negative 1.64. Well, what about 99%? Well, 99% would mean that half of 1% was here, 0.005, and half of 1% was here. So let's see, at the bottom tail, for z-score we need at the bottom for 0.005, 0.005 is going to be 2. Let's see, 5. Where's 0, 0? Oh, it's right around here. So it would be 2.5, 0, 1, 2, 3, 4, 5, 6, 7, 8. We'll call it 2.58. 1.64, 2.58, and the one we're going to use the most frequently, 1.96. Okay, so that's where those three numbers came from. That's where we get those. They originate from that formula that represents the distribution, which is summarized in the ZTable. Okay, so now, so that's what we're going to use. So now, if I look at my repeated samples, right? For instance, if I take, I'm going to get a fresh page here, just so we don't have all that scribble on there. Okay, so now, if I were to say that, okay, this is my distribution, again, of sample means, not my population, but my sample means. Okay, if I were to say before, let's say that our first distribution, the population, right, that first one that we're working with, let's say the mean was 100, u was equal to 100, and the standard deviation was equal to 10. Okay, so now let's see what would happen here when I take a repeated samples of size n equals 25. What would happen in this case? Well, our sample distribution now, if I took many, many, many samples, our sample distribution now would have a mean of 100, right? And it would have a standard deviation of sample means equal to the standard deviation of the population over the square root of the sample size. Okay, so again, what is this? That's the standard error. It would have a standard error of sigma over the square root of n. So what's sigma? Sigma is 10. Sample size is 25, right, which is 5. So what is this equal to? This is equal to 10 divided by 5, which is equal to 2. My standard error, my distribution of all possible samples from this population of size 25 is now, the width of that now, the standard error, the variability is now 2 instead of 10, which it was for the population. So that means if I go 2 standard deviations below and 2 standard deviations above the mean, 95% of the possible outcomes I might get are going to be between, let's see, 100 and 2 below the mean, which would be 96, and 2 above the mean, which would be 104. Okay, but again, we like to be more precise, so it would be 100, right, minus 1.96 times 2, and 100 plus 1.96 times 2. Okay, just 1.96 is a more accurate range for 95% than 2 is. Okay, so that's how I would figure out how wide this whole thing is. Well, now we're going to go ahead and apply this. We're not going to take, this is if we took an infinite number of samples, if we took many samples. That doesn't happen in real life. We never actually see this distribution in real life, because we would never go back and do 1,000 samples from the same population. Might sample 1,000 people, but we wouldn't repeat that 1,000 times. So instead, we use this relationship between the standard, the distribution of the population, and the distribution of the sample means to understand how what kind of information a single sample gives us, how reliable a single sample can be. And that's where we get into our confidence interval. So now what I'm going to do now is I'm going to say to myself, okay, I am going to make believe that my population, again, I'm going to take the same population, mu is equal to 100. Matter of fact, mu is equal to 100, but we don't know that, do we? But let's say I do know that the standard deviation is equal to 10. I'm going to say, well, let's say that I take a sample size of 100. And when I take that sample size of 100, the result that I get, this is one result only, we only take sample once, right? This result turns out to be 99, okay? Well, we know that the population mean approximates, the sample mean approximates the population mean, right? We think that they should be the same or close to the same. Okay, so, and in fact, the bigger the sample size is, the more reliable that this statement is, right? Because you're taking a bigger sample size, less chance that you're going to get a preponderance of people that are under the mean or above the mean. You're probably going to get closer to the same. Okay, just like if you flip two coins, right? The likelihood of both of them coming up heads is not very unlikely, even though the average should be 1 and 1, right? But if you flipped 100 coins, well, then you'd expect to get a lot more closer to 50% than if you just flip two coins. Okay, so at any rate, so now we're going to apply this now. We're going to say to ourselves, okay, my sample mean, see, I don't know this guy up here. I don't know that 100, right? That's unknown to me. My sample mean, X bar, came out to be 100. Okay? 99. Right? My sample mean came out to be 99. Okay? So now I know that if I take one sample, do I know the population mean? No, I know it approximates the population mean, but I really don't know what the population mean is from that one sample. So this is kind of like not very helpful to me. If I know that my sample of 100 people gave me a mean of 99, well, gee, what does that mean to me? I mean, how useful is that to me if I don't know how accurate that prediction is? In other words, say I get 99, and does that mean that the sample mean could be 150? Does that mean that the sample mean could be 99.1? Does that mean that the sample mean could be 80? What does that mean to me that when I took this sample of 100 people, that the sample mean came out to be 99? It's not very useful to me unless I can put it into perspective in terms of the probability that this is how accurate this reading is, or how probable it is that the real population mean is close to this number. Okay, that would really make this result more useful to me. Okay, and that's why we use confidence intervals. Confidence intervals give us a measure of how likely it is that the population mean, the real mean that we're interested in, we're never really interested in sample mean, we're really interested in only doing this to know what the population mean is, that would give me a result that makes some sense, is that useful to me, or how precise this answer is. Okay, and that's where we use the confidence interval. And what's the confidence interval? The confidence interval, we know we got a mean here of 99, right? We know that in this population, if the population standard deviation is 10, we know that the distribution of all of the sample means, right? All of these sample means, the distribution would be sigma over the square root of 10, over the square root of the sample size, 100, okay, which is equal to, 10 over 100, square root of 100. 10 over 10 is equal to 1. So our standard error is 1. So we know that the distribution of all samples from this population is a standard error of 1. We know that 95% of if I took a repeated samples from this population, as we did before, 95% of the time they would be between two standard errors below the mean In other words, there would be 2 standard errors below the mean and 2 standard errors above the mean. Okay, so we're going to use that information now. We're going to say to ourselves, okay, I know the population standard deviation. I don't know the population mean. So I'm going to say to myself, okay, let's see what range that would give me. 2 standard deviations below the mean is 97, right? In reality, it's a little bit less than that, right? Because a little bit more than that because we use 1.96 instead of 2. But for the moment, I'm going to use 2 or 101. Okay, so this is 2 standard errors below the mean and 2 standard errors above the mean, 2 standard deviations to the mean above and below. So I'm going to predict and say to myself, since I understand the way that the distribution for the mean is, the distribution of repeated means for this population are distributed because I know the sample standard deviation, because I know the sample size, I can predict that I would expect that the mean of the population is going to be within 2 standard deviations of any sample that I took of that size. Well, I'm going to assume for a moment that 99 is the population standard deviation mean. Okay, and I'm going to add and subtract 2 standard errors from it, and I'm going to get 97 to 101. Okay, well, what have I done here? What I've done is I've given myself a range of numbers that represents that if this is really a true sample mean, that's where I would expect the distribution of this uh, 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 um, of these repeated samples to occur. Between 97 and 101, I would expect 95% of the time I would get results between those two. Well, I can't really use it that way, can I? Because I really don't know what the population. This was all based on the population mean, right? We would expect 95% of the results to be between 2 standard deviations above and below the population mean, not the mean I got on this particular sample. So I'm going to use this a different way. I'm going to say to myself, okay, I got 99. I'm going to use that kind of as a placeholder and call that my mean. Okay, but I'm going to add and subtract 2 standard deviations from that number and say that my range, 97 to 101, I don't really know that 99 is really the true population mean, but I'm going to say that at least I'm 95% certain that if I look for the population mean or I discover the population mean later on, that it's going to be between 97 and 101, hence our confidence interval. The mean that we got from our sample was 99, but our confidence interval is 97 to 101. In other words, we got the result 99, but we're not sure if that's really the population mean. Might be close, but we're not sure. But we're 95% certain that the true population mean is between 97 and 101. In some ways, this is more useful than just knowing what the result is of the sample mean. Okay? Are we okay now? Are we still all on the same page at this stage? Any questions at this stage? Okay, good. Right, so that's really what we're doing here. We're trying to predict, we're trying to establish a range within, how did I get 99? I made that up. I made 99 up. I just said to myself, I took a sample of 100 people from that original population that we started with, which was 70 to 130, I guess it was. And I just said, let's say the result of that one sample. Remember, we in real life we don't take repeated samples. We got one shot. We do a study. We got one shot. We take our sample and we take our average. Okay, so that's where that 99 came from. Could have been 98. And as a matter of fact, funny you should mention that. But you know, one out of every 20 times, 5% of the time, I might get a result that's outside of 97 to 101. That's our error, right? That's okay. We're only that close to the mean 95% of the time. 5% of the time, I'm going to get a result that's outside of our confidence interval, right? And then I'll miss the mean. In other words, well, you use 1.96 all of the time. Okay, basically from this point on, we're not going to use the empirical formula anymore. We're going to use the actual z-score, which represents 95% of the confidence interval. I'm using 2 here because it's just easier for me to do that rather than slow things down and use 1.96. Okay, so, and what do we use for 90%? For 90%, we use excuse me, for 90%, we use 1.64, and for 99%, we use 2.58. Okay, now I'm going to write this formula out, this confidence interval formula. Okay, I'm going to write it out a little bit more formally. Okay, what is the confidence interval formula? Okay, I'm going to click here. Okay, so confidence interval formula is X bar plus or minus. We're going to add and subtract from this 2 standard deviations below, 2 standard deviations above, except we're going to use the z-score for our level of acceptable error, alpha, right? Okay, so it's really alpha over 2, kind of. I'm going to explain that in a second. Okay, our z-score times our standard error. Okay, so if we're going to do 95% confidence interval, right, it's going to be X bar plus or minus 1.96 times the standard error. We're going to do a 90% confidence interval. It's going to be X bar plus or minus 1.64 times the standard error. If we're going to do a 99% confidence interval, it's going to be X bar plus or minus 2.58 times the standard error. Okay. Anybody remember what we call this number in here, this combination of the z-score and the standard error? That's right, margin of error, because you kind of, makes sense, right? Because, it's plus or minus this, right? Kind of the way you would normally, a normal person would refer to margin of error. Okay, good. So which of these three, 95% confidence interval, 90% confidence interval, 99% confidence interval, which is the widest range? Is it the 90? It's the 99. Right, it's 99 because we're multiplying it by the biggest number, the 2.58. That makes sense intuitively because if you have a wider range, you're more confident that the true mean is going to be between those two numbers if you accept a wider range around x, right? But if you don't like that, you want a narrower range, right? Then if you use a 90% confidence interval, this is a narrower range, but you're less confident. You're only 90% confident that the true mean is between the two of those numbers. Okay, so that's kind of the trade-off that you're making there. If I want to increase my level of confidence from 95%, and I want to, let's say I'm doing 95% confidence interval, and I want to make this range narrower, right? But I'm not willing to go to 99%, and I'm not willing to give up confidence. What can I do to make this range narrower than it is now? I can't change the 1.96 because I need that for the 95%. I can increase the sample size. Exactly, because this is sigma over the square root of n. So if I increase the sample size, it makes this a narrower range. I don't give up any level of confidence. Good, excellent, great. So now we can go ahead and apply this. We can apply this to a number of different situations. I just want to mention one thing before we move on, and that is that we can do this same thing with proportions. Okay, proportions are situations where, for instance, I might tell you that we sampled 100 Democrats, and of those 100 Democrats, 52 of the Democrats are going to vote for Hillary Clinton, right? And so the proportion of Democrats that in our sample, the proportions of Democrats that are going to vote for Hillary Clinton are 52 out of 100. Okay, so our P cap, okay, we put a little cap on that, kind of like we put the bar on top of the X. Our sample proportion is 0.52. Okay, well, if I go back to the same population of 100 Democrats and randomly sample another 100 Democrats, well, I might get a value higher than 52% or value lower than 52%, but unsurprisingly, it's also going to be normally distributed. And I got the same problem with this proportion. How certain can I be that the real population of all Democrats is 52% if I only took a sample of 100 of them? Well, we do the same thing with P cap, except with P cap, 95% confidence interval is going to be P cap plus or minus 1.96 times the standard error. And the same thing happens over here, 90%, 99%. So you're going to change the z-score. Okay, but with p cap, what we're going to do here, the standard error is going to be equal to the square root of the proportion p cap times 1 minus p cap, right? Hopefully, if you have the population, well, if you have the population proportion, you'll do it. Okay, over the sample. All of this is underneath the square root. So for instance, this would be 0.52 times 0.48 divided by 100. You resolve all of that, and then you take the square root. It's not a separate square root for the sample size. Then plug that in here, and that would give you a confidence interval for the proportion of people that are going to vote for Hillary, Democrats going to vote for Hillary Clinton. So that might wind up being 0.52 plus or minus, let's say 0.04. I'm making that number up. I didn't actually do the calculation. And what is that? That's your margin of error. That's what you see in the polls all the time. There was a 4% margin of error in this poll, so on and so forth. And that's where that comes from, basically. Okay, so I'm going to move on, and we're going to start working on some of the problems with this. Just one more thing. You see alpha over. We mentioned alpha. Alpha is the probability of a type 1 error. Right? Type 1 error is when you're wrong. You make a prediction based on your confidence interval or on your hypothesis, and you're wrong. Well, that type 1 error, in this case, if we're going to choose a 95% confidence interval and the mean winds up outside of this range in the lower 2.5% or the upper 2.5% for a 95% confidence interval, that's a type 1 error. What's the probability for a 95% confidence interval of a type 1 error? Well, alpha is equal to 0.05, 5% chance of being wrong. If you're 95% confident, 5% chance of being wrong. If you're 99% confident, alpha is equal to 1% for a 99% confidence interval, right? Now, again, half of it is in the lower tail, half of it's in the upper tail. So a lot of times you'll see somebody write the z-score for alpha over 2, right? Well, what does that mean? Well, the z-score alpha is for 95% confidence interval. Alpha is 0.05. So the z-score for alpha over 2 is the 0.025. In other words, that's the probability of being in that lower tail. So it makes it a little easier to say, oh, that z-score has got to be negative 1.96 or positive 1.96, right? So you know that where to look for it on the z-table. So that's why sometimes you'll see that little summary alpha over 2 underneath that z-score. And you know for 95% confidence interval or 5% chance of being wrong, that means that in each tail you have 2.5% or alpha over 2. Like, a little confusing, right? But hopefully you won't run into that problem. Great question on what's the probability of making a type 2 error. Type 2 error, a little easier to explain when we do hypothesis testing. But a type 2 error is when you fail to come to a conclusion when in other words, find a difference between two groups, the way a drug works versus a placebo works. When there is really a difference between the way the two work, that the drug really works, that you fail to recognize that difference. So you don't have enough information, you don't have big enough sample size, and so on and so forth, and you fail to confirm that drug is effective. Type 1 error is you say that, gee, this drug is effective, and it's working, and you're wrong. That's type 1 error. You want that to be really low because you don't want to base a diagnostic test or a drug use or something like that unless you're really certain that the drug is safe and going to be effective, right? So, but you're more willing usually to make a type 2 error because you can always go back and take another look at it with a bigger sample size and so on and so forth. But a type 2 error is a different kind of error. Make more sense when we talk about hypothesis testing. Okay, so that's what we talk about for alphas is the possibility of type 1 error, or you can also look at it as a probability of our sample size not capturing, our confidence interval not capturing the population mean. Okay, so let's move on to some actual problems. Okay, let me get this out of the way for a moment. Okay, so Let me see. Somebody mentioned one of these before. Let me back up a little bit. Maybe I should start with that one. Make sure I get to it. I gotta go scroll back here. Back.